Today, I'll be trying out for myself the 2025 H2 Chemistry Paper 1. Honestly, I've been hearing so many mixed comments from all around the internet and from some of my students. Some of them saying that it was the easiest paper they ever had, and some of them saying that, oh, this was a very tough paper and a very tricky paper. So I'm quite excited to see what exactly is in store for this paper 1. So I've decided to give this a go myself, and I'll be giving my honest review about the standard of this paper by the end of this video, so do watch to the end to check that out. I'll also be putting a timer, use it as a way to gauge how tough a question is and how much time I'm actually spending on each question and overall for the whole paper when I'm doing it from scratch. You also see me try to do this in 1 hour, so I'm kind of like battling against time just like how you all did during your A-levels as well. Hi, I'm Brendan, and I've been helping students like you achieve their mastery over chemistry over the past 8 years, and I hope that you can learn something from me today. If you like this kind of content, be sure to give this video a like and a subscribe. Would really appreciate that. Okay, here we go. I'm gonna start the timer right about now. Really excited. Okay, let's go. So we have here, the table shows the nuclear number, the number of neutrons, and the number of electrons in 4 different particles. So you got nuclear number of neutrons, number of electrons, which pair represents atoms of 2 different elements. If there are 2 different elements, okay, I would assume that they have to be a different number of protons, and I'm going to ignore a lot of these notations over here. So if you take the nuclear number, you just take nuclear number minus the neutron number, and you will get 207. This is indeed 85. Okay, and then this is 82, right? And 209 minus 125, this is 84. And then 210 and 127, this is 83 over here. They seem to have all the different number of protons. It's 4 different particles. The bridge pair represents atoms of 2 different elements. What?
You what?
They all seem to be very different. But if you look at the number of electrons, it's 84. This seems to be an ion. This seems to be an atom. Okay, because they're looking for atoms. Okay, and then this is an ion. Okay, and then this is an atom. So I'll probably have to pick X and Z. Oh, there you go. Okay, so answer is D over here. Okay, a bit rough start. I'm a bit rusty. Okay, use of data booklet is relevant to this question. The charge on 1 mole of particle Q is 96,500 C. Okay, so 1 mole of particle R has mass of less than this. So which statement is correct? This Q could be a proton only. R could be a proton, a neutron, and an electron. If Q is a proton only, that means this is actually just H plus. Can Q be H plus over here? Let me think. 1 mole of particle R has a mass of less than 0.500 grams. If 1 mole of particle R has a mass of less than 0.500 grams, if you're using 1 mole, for example, 1 mole, if you're taking 1 mole of like a proton, a neutron, and an electron, then this has to be, if I remember correctly, this is 1 mole is actually consists of 6.02 times 10 to the power of 23 number of particles, and each particle of an, okay, we know that R, okay, we know that a 1 mole of a proton and 1 mole of a neutron is like basically a 1 and a 1, right? So if this R has a mass of less than 0.500 grams, then this can't really be the answer here. So I wouldn't pick this as answer here. Then Q could be a proton only, so R could be an electron only. So Q. Okay, what I know for R for sure is that it's definitely not a proton and a neutron, that's for sure. Because 1 mole of a proton, 1 mole of a neutron is 1 gram. So definitely anything that says that R can be a proton and or a neutron or a combination is wrong. So R has to be an electron. So I'll cross out A and C over here. And then for Q, it says that a charge on 1 mole of particle Q is 96500. So it has to be, since it's a plus sign, it has to be a positive one. So this answer is probably B. It has to be a proton. It cannot be an electron here. Next, uranium hexafluoride. You have 6 as a bonding part of this. Thallium iodide has a melting point of this. It conducts electricity when molten. Okay, if this is molten, what are the structure of these two substances in the solid state? Okay, this looks very ionic. Okay, it conducts electricity only when molten. So I have to pick that it has to be ionic, yep, so I wouldn't have this. And then for UF6, it has a boiling point of 330K, so it confirmed cannot be ionic, so it has to be simple molecular structure over here. So answer is D. Okay, this is how you save time in the exam. Next, what's the correct statement with a correct reason about the trends in ionization energies in the periodic table? So it says, first, boron has a lower first ionization energy than beryllium because the 2p electron is more shielded from the nuclear charge. For this, 2p electrons more shielded from nuclear charge. And this looks correct. Indeed, I would think that this is correct. Nothing seems to be wrong about this. Let's look at the others. Copper, nickel have first ionization energy. They only differ by this because they lose an electron from a 3d orbital. Well, it's not just because of that. There's also the difference in protons. So this is wrong. The first ionization energy increased from oxygen to neon across period 2 because each successive element has one more electron there. Yeah, but the first ionization energy doesn't increase because of the one more electron. It increases because of the nuclear charge. So this is wrong. Second ionization energy of phosphorus is greater than first ionization energy of sulfur because the ions form the same electronic configuration. No, this doesn't affect the nuclear charge at all. So this is wrong. So I'll pick A here. Yep. So moving on. L and M are chlorides of elements from the third period. Both L and M produce a color solution when added to water. And third, the table below shows more information about L and M. Okay, so this is talking about periodicity most likely. Okay, they produce a color solution. So which statement best describes the nature of the aqueous solutions? So if this is a high electrical conductivity of the molten chloride, then definitely it's an ionic. So it's ionic. This produces an ionic chloride. And this one over here seems to be like a simple molecular structure. Okay, so they say best describes the solution. So it says both solutions are neutral. This is definitely no, because if M is PS or Cl, right? Definitely it's you'll give an acidic solution. You'll give a HCl in the background, or yeah, basically. Both solutions are alkaline, definitely no. Okay, we already said M is most likely acidic. Then solution of L is neutral, solution M is acidic. Yup, that's correct. And for L, I would say this is, if this produces like, for your ionic chlorides, it's only NaCl or MgCl2, and yeah, they're mainly quite neutral lah. Maybe this is a bit acidic, but I would probably be okay with this. This is definitely wrong. This is definitely wrong. So answer C over here. Next. Okay. Then it says use of data booklet is relevant to this question. Iron trioxide can be reduced to iron using the sequence of reactions shown. Too many notations here. I'm trying to ignore it. What's the minimum volume of oxygen measured at STP? Oh, okay, this is very important. Yep, STP. Okay, because definitely, you know, 1 mole equals to 22.4 dm cubed at STP. So required to produce 0.422 grams of iron. If this is 0.422 grams, okay, so we need to circle where the iron is. So the iron is over here, right? So we want to produce this, and the minimum volume of oxygen would be found here, right? And then you have to look at the sequence of equations of how they link together. So this CO2 is linked over here, okay, and this and then this CO is linked over here, right? So that's how the equations are kind of linked. So you have to work backwards from there. So definitely if it's 0.422 grams of iron, okay, gotta look at that periodic table here. So the number of moles of iron is equals to 0.422 divided by the molar mass, which is 55.8. Okay, so let me just quickly. Oh, the pressure. Oh, okay. This is 0.007563 moles. Okay, so you know the NCO is just 3/2 times this. So just by mole ratio, this is 0.01134 mole. Okay, and because of that, you know that the number of moles of CO2 by mole ratio is just half. And if you look further on, this is 1:1, so it's just this equals this, so this is 0.01134. So just times half here, 0.005672 moles. Okay, and then after that, I'll just times 22.4 dm cubed. So I just 22.4 dm cubed. This looks to be about 0.0. No, this is 0.1271 dm cubed. And I'll pick the closest answer, which is A over here. Yep, so I'll just get A. 129 cm cube around there. Oh, it is the minimum volume, so I expect A to be higher. Okay, next. Okay, calculation takes very, very long. Which pair is not a Bronsted-Lowry conjugate acid base pair? Oh, this is not. Okay, so I have to choose one. BH3 and BH4 minus. What? One should be a proton donor and one should be a proton acceptor. This does not really look like it. There's no positive charge. Okay, I'll just skip this. Let's look at B. H2PO4 minus and HPO4 2 minus. Yep, this looks like it donates a proton. So remember, we're looking for a proton donor slash proton acceptor. Yep, this looks like it donated a proton to form this. This one looks like it donated a proton to form this. This one looks like it donated a proton from this. So the answer looks like A. Can't be B, C, or D. These look like proper pairs. Next, hydrogen oxygen fuel cell releases energy by oxidizing hydrogen at one electrode and reducing oxygen at another electrode. Okay, this is very important. The ions produced then combine to form water. So they use this, and then which row correct shows the signs for delta H, delta S, and delta G. Oh, okay. So just looking at this equation, you're going from a gas to a liquid mainly. So delta S is definitely negative. So I would cross out D already. And then for delta H, they say it releases energy. That's right. So it has to be negative. So definitely not C already. And then for delta G, it looks, they say this is a fuel cell. And the only way to do that is, you gotta know about delta G equals to delta H minus T delta S. So if delta S is negative and delta H is negative, well then it really depends at room temperature, right? Whether this is spontaneous or not. The other way to do this is to think about, I don't think I can find out the sign from here, right? If they're both negative, then it really depends on the magnitude of delta H and delta S. They're not even saying if it's spontaneous or not. So I have to use delta G equals to negative NFE over here. And if I look at my data booklet, so you are getting H2O, right? So the E reduction, you are reducing oxygen at the electrode. So if you're reducing oxygen at the electrode, this has to be plus 1.23 V. And then if you're oxidizing hydrogen, this has to be, it probably is just 0.00. And if it's red minus ox, then my E naught cell seems to be equals to plus 1.23 V. And because of that, if it's negative NFE, this looks like my delta G has to be negative. Yeah, if you plug this in here, delta G is negative, so it has to be A. There you go. Okay, next. The Boltzmann distribution and activation energies for homogeneous gaseous reactions under different conditions J and K are shown. Which change in conditions will result in the changes from J to K? This is very typical of a decrease in temperature. I know this definitely from this Boltzmann if you go from here to here lah. Right, this is a decrease in temperature, but maybe there's something else. So this is definitely wrong. It's definitely wrong. Okay. Oh, and they say maybe if you add a catalyst. Oh, okay, yes, for J to K, you're going here, so you're lowering the activation energy. So answer is C. Okay, next, these are time savers over here. 10. Nickel reacts with carbon monoxide on heating. An excess of nickel is placed in a flask containing CO. Okay, this is definitely an equilibrium question, so I should probably use an ice table. They are putting a lot of pressures and volumes and temperatures as well, so maybe it's ideal gas law. Excess of this is in a flask containing this. After no further change, the pressure in the flask is 0.37 atm at the temperature of this. This is the total pressure at temperature of 350 K. So what is the partial pressure of CO gas in this equilibrium mixture? If they use 1 ATM, right, at the start, yeah, so I would probably just do an ice table over here. So let's just quickly do an ice table. Again, we don't have to think about the nickel, yeah, because it's a solid, right? So they are saying that you started with 1 ATM over here, and then the pressure total afterwards is minus 0.37. So here you minus x, here you plus x, so 1 minus x and x over here, right? And then they're saying that 1 minus x. Oh no, sorry, you have to use more ratios here. So this is minus 4x. So they're saying 1 minus 4x plus x actually gives you 0.37. So you know that actually here 3x equals to 0.63. So x equals to 0.21. So this means that when this 0.21 is, yeah, this means that 0.21 and 0.21, so what's the partial pressure of CO gas in the equilibrium mixture? So it's just 1 minus 4x, right? So it's just 1 minus 4, 0.21. This equals to 0.16 ATM. So this looks like A. Yeah, I would pick A. Okay, next, for this next question up here, so they say the graph shows how delta G changes with temperature for the reaction shown. This delta G changes with temperature. Okay, so there's a graph of delta G changing with temperature, very interesting. Okay, and it's getting, since it's increasing, it seems to be less and less spontaneous as temperature increases. Okay, so they say equimolar amounts of this were introduced into a sealed container and allowed to reach equilibrium. Okay, at which points will the concentration of H2 be greater than the concentration of H2O at equilibrium? This really depends. It seems to be spontaneous all the way until this point 2. You see this point as 0. This most likely shows that this is at equilibrium, right? So if this is the case, if this is at equilibrium, it really depends on what the... Yeah, it could be at equilibrium, but to know the... If you want to know the correlation between delta G and K, right, because you want to know the K value, then delta G basically equals to negative RT ln K, right? And it seems like when delta G is negative, RT ln K is a positive value. Okay, so basically for the concentration of H2, right, to be greater than the concentration of H2O, your K needs to be greater than 1. So if that is the case, when K is greater, you see, when K equals to 1, right, ln K basically equals to 0. Okay, so and then when your K is greater than 1, right, let's take for example, I would take that did they tell us the temperature over here? Oh yeah, they tell us a few temperatures over here. Okay, so you probably have to calculate it. It probably is not it's probably not 2 and 1. Yeah, because when K goes to 1, that means the concentration of H2O and H2 is probably the same. It's probably not when K is... Yeah, when K is greater than 1, right? You can work backwards to it, and then you can see this delta G over here. Okay, another way is, I probably use this way, it's much easier, is I'll just calculate it straight up. So let's look at 0.4 for example. So 0.4 is 500K at negative 20. So negative 20 equals to, I'm gonna give R, and then this is 500 temperature Kelvin ln K. And I'll just calculate K over here. Right, so this is just so I'll be able to calculate ln K actually equals to 20 divided by R is 8.31 times 500. Okay, so I'll get like 0.004813. And in this case over here, K seems to be, yeah, this seems to be 1.005. So this fulfills the criteria that K is greater than 1. Okay, so definitely 4 is correct. Let's look at 3 over here. 3, okay, let's just use a value like negative, this is 770K, right, at negative 10 delta G. Okay, so let's use that at negative 10 equals negative R, 770 temperature ln K. So your ln K over here equals to 10 divided by 8.31 times 770. Okay, this is 0.001563. Okay, and then this, if you just plug this in, actually equals to 1.002, which is greater than 1. So this says that 3 is also correct. And we know that 2 is definitely wrong. Okay, as I explained just now. So if 2 is wrong and 3 and 4 is correct, answer is definitely D over here. Okay, whew. Tough calculation question. Okay, next. So the diagram shows compound X over here. Which molecules have the same empirical formula as compound X? Oh, this is just a counting question. It's so annoying. So let's just count 1, 2, 3, 4, 5, 6, 7, 8 carbons. So it's C8, and then there's 2 oxygens, and then how many hydrogens? There's 3. Okay, 3 plus. I'm just gonna erase this. And I counted number. So I'll count the number of hydrogens here. 3. And then there's 1 here. 4. There's 2. There's 2. I just write the number of hydrogens first. Like this. Okay, so there's 3, 5, 7, 9, 10, 12. Okay, it's C8H12, O2 over here. So which molecule has the same empirical formula? This is so annoying. Is there maybe a shortcut somewhere? Let's just count number of carb. No, you can't do that. Empirical formula here is C4H6O. Okay. Maybe I start with the simpler ones. So for 2, okay, let's just look at 1 first. So this is 1, 2, 3, 4, 5, 6, 7, 8. This is 8 carbons. And then there's 3, 2, 1, 1. Oh no, sorry, 2 here. 1, 1, 2. So this is just 5, 6, 10, 12, O2. Yep, this looks correct. Okay, for 2 over here, this is C4. And then there's 2, 1, 1, 2. So this is H6O. Yep, this looks correct as well. Okay, and then 3. Man, they're really good at giving time wasters here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 carbons over here. Count number of hydrogens. I'll just put the number of hydrogens to make this clearer. In a skeletal structure, it can be quite confusing. So there's 5 here, 7, 9, 10, 12, 14, 15, 16, 17, 18, 20, 22, 23, 24. So this is H24. And this is O, there's 4 O's. If you simplify this, C4H6O. Yep, they really wanted you to do this. So answer is A. Okay, next. A saturated solution of zinc 2 hydroxide has a KSP value of 2.3 times 10 to the power minus 14. What's the concentration of this solution? If this is KSP equals to zinc 2 plus OH minus square. What's the concentration of this solution? Yeah, then this one you have to use the solubility equation. So you know that the concentration is actually just S and S square over here. Okay, so the KSP is actually equals to 4S cubed. So if you want to find S, okay, this is just 2.3 times 10 to the power minus 14 divided by 4. Then you just cube root the whole thing. I think that's how you do it. I don't think there's any trap around here. It is a saturated solution. Okay, so let's just put this all in. And we try to get the answer here. And they say the answer is 1.792 times 10 to the power minus 5. Don't think there's a trap here. Can't see. Seems like it's B. Okay. Which types of reaction occur in the two-stage conversion of 1 bromopropane to 2 bromopropane over here? Two-stage conversion. This is okay. I guess I can draw this out. This becomes something and then become this. Let's just look at some of the options. Substitution followed by elimination, definitely no, because this will form the double bond in the end. There's no anything that ends with elimination looks wrong. Okay, C, elimination followed by addition, form the double bond, and then you electrophilic addition. This looks correct, yeah, because maybe I can form like this, and then I do addition, and then elimination followed by substitution. This looks wrong. Okay, yep, pretty straightforward question. Next, compound P has a molecular formula of this, C4HAO2. So how many? It contains only one functional group, which can be a carboxylic acid or an ester. So they tell you already how many structural isomers. Oh my goodness, it's so annoying. Okay, so you have to. Let's look at the easiest one, which is 4 carbons. Let's start with a carboxylic acid group, right? So it's 4 carbons. It's like this, or like actually, you know what? There's not enough space over here, so maybe I'll just do my working here. Okay, so this has to be 4 carbons. C8H8O2. Does this satisfy the criteria? H83221. Yeah, this looks okay. So there's only one pi bond involved. Okay, the other one I can think of with a carboxylic acid is like this. I don't think there's any other carboxylic acid variations over here, because I immediately think about branching, and the carboxylic acid group has to be at the end. So you just have to do one form of branching. I don't think there's any other variation. Let's look at esters. So this is esters is very interesting because you can 3 carbon 1 carbon. So let's do 3 carbon 1 carbon first. So this is just like this. Okay, there's 3 carbon 1 carbon, then there's 2 carbon 2 carbon, and then there's 1 carbon 3 carbon over here. So it can be like this. This. Okay, so I would say that this is this looks like it is 5, I think. I mean, I don't think that they will give 6. I can't think of any other isomer that's like that. Is there 1, 2? If I remember correctly, can I do a 6? Oh, I can do branching here, I guess. Yeah, I can do branching here. So this could be, it could be like this. Yeah, I would say this is probably the answer then. So yeah, I can do 6. Okay. Okay, so yeah, okay, I'll change my answer. This is probably 6, yeah. Okay, next. 16. Which gas takes part in the production of both photochemical smog and the formation of acid rain? Both photochemical smog and acid rain, so this has to be nitrogen oxides, because this one is nitrogen oxides and hydrocarbons. Yeah, answer C. It's clearly. Okay, 17. An unknown organic compound is tested in warm silver nitrate solution. This smells like halogen derivative topic. Okay, no visible result is seen after 1 hour. Then they see the experiment, each make a comment. This compound is definitely halogenoarene, but it is not possible to state which halogen is present. Is it definitely a halogenoarene? No, it doesn't have to be halogenoarene. If it's a halogen compound, you could have a CF bond. Okay, and this wouldn't work out as well, even a halogenoalkane. So this is wrong. I hate it when they say that this is definitely halogenoarene. Yeah, this compound is definitely not a halogenoalkane. That's not true as well. It could be a halogenoarene as well. So they're both kind of wrong. So this is B. I doubt that this is correct. Yeah. 18. In which reaction does the organic reactant behave as a nucleophile? The organic reactant behaving as a nucleophile is, okay, it has to be the organic reactant. So if you look at A over here, this is a substitution, no way. It's free radical sub, there's no nucleophilic. Here is nucleophilic sub, but this isn't the nucleophile, this is the nucleophile, so this is wrong. Let's look at this one. Yeah, this is electrophilic addition, where this is the electrophile. So in some sense, if this is the electrophile, you know that this is definitely a nucleophile over here. Usually they come in a pair. Let's look at the other one. This is nucleophilic addition, but this is the nucleophile. So this can't be the answer. So it has to be C, if I'm not wrong. Okay? Chlorine gas and ethane react together by a free radical substitution mechanism that occurs via a series of reactions. In reaction K, one species produces two species. What? Okay, free radical. Sub. So this is in your alkanes chapter. In reaction K, one species produces two species with exactly half the mass of the original species. It produces two species? What? This makes no sense. In reaction L, two species of identical mass interact to produce one species of twice the mass. Oh, and then it's just initiation, propagation, termination. Yeah, if I'm thinking of two species of identical mass, and then it produces one that's twice the mass, I'm thinking of something like this. So this is probably a termination reaction. So definitely L is termination. So I'll cross these two out. And then it's between initiation and propagation. If one species produces two species but with half the mass, then I'm thinking about this, right? They just like this, right? And then they just split like this, and then it's exactly half the mass. So this seems like initiation. So I'll pick B. Okay, next. 20. Which reagent and catalyst convert benzene into G? This is benzene into G. That's nuts. How do you get from here to here? You can do like a double Friedel-Crafts, because it seems like you do Friedel-Crafts one time, alkylation, and then but then the product, so you get something like this. Oh yeah, kind of like, yeah, you get something like this, and then you do a further substitution with benzene again with the catalyst. So you could do one with two CLs. So the target is, I would choose something like this. This seems pretty good. Yeah, and then you Friedel-Crafts and then you do it again. So this seems like the answer. So this is CH3, CHCl2. Yeah, so I definitely wouldn't pick these two. And then catalyst, it's definitely AlCl3. Can't pick this. Okay, so this is A. Okay, 21. An ester J is hydrolyzed by heating with aqueous sulfuric acid. This seems like a... Okay, it's like a little elucidation question. So annoying. Okay, so an ester J is hydrolyzed by heating with aqueous sulfuric acid. Okay, so this hydrolysis first. The ester, so you know the ester would give a carboxylic acid, most likely, plus a alcohol. How much time do I have left? Oh, okay, around 26 minutes. The final mixture of products contain only one organic compound. Final mixture contains, they say it's heated under reflux with acidified potassium dichromate. So this oxidation. So you oxidize the alcohol, the carboxylic acid, and then you only get one compound. Oh, I see. So in the end, the carboxylic acid and the alcohol, they have to be like kind of symmetrical. They have to have like the same number of carbons and the same rough structure. So what could ester J be? Okay, let's take a look at this. CH3, CO2, C2H5 is like... Yeah, so this is like two carbons and two carbons, right? Most likely it'll be the same in the end, because you produce like the carboxylic acid and the alcohol, and then the alcohol will just oxidize to become the carboxylic acid with two carbons each. So this looks correct. Okay, this one CH3, CH2, CO2. No, this is definitely not. If you can see over here. Right, this is CH, CH3, you see this structure over here is definitely different from this. In fact, this would give a ketone. You see? Yeah, this is... I can already see it. You see, you get this. And then this will further become a ketone. It's not even a carboxylic acid. This is wrong. So 2 is wrong. If 2 is wrong and 1 is definitely correct, then it has to be B. I'll pick B immediately. Let's look at 3. This is look, this is 4 carbons long and 2 carbons long here. There's no way. Okay, I'm good. We'll move on. Okay, which molecules may be used in protein formation? Ooh, diaminohexanoic acid. Let's draw the base first. So this is 2, 3, 4, 5, 6 hexanoic acid, and in the 2,6 position. What? This is hexanoic acid. How can it be? Protein formation. Oh, it's just it's just an amino acid. So then why is it in the 6th position? Oh, no. Okay. So it's two 6th position. I forgot this is 1, 2, 3, 4, 5, 6. Okay, so this is just NH2 and this NH2 over here. Yeah, okay. Yeah. Bit rusty. Okay, and then they say it may be used in protein formation. Yeah, because this is a carbon with a carboxylic acid group and a NH2. So I'll pick 1. Okay, 2-amino benzoic acid. Benzoic acid is like this, no? This doesn't satisfy the criteria to do peptide linkage. This is an amino acid. Wrong. Okay. And then 3-amino propanoic acid. Propanoic acid is like this. 3 aminos here. Yeah, this can't be it. You can't use 2 and 3, so it has to be B. Okay. Which statement about ethanoyl chloride is correct over here? Okay, so this is acyl chloride, so let's bear this in mind. And we only know the functional group to base this off. Okay, it says it reacts with amino ethane to produce this. Ooh, okay. When your question gives you something like that, let's just draw it out. So ethanoyl chloride is like this. Then the amino ethane is like this, right? Okay, this will give you NH like this. Is this C2H5NHCOCH3? Yeah, this looks correct as much as I say. Okay, let's look at others. Reacts with phenol to produce this. No, there's no. Wait, reacts with phenol. Huh? Oh, there's only one O here. Yeah, it can't be. It has to be an ester. So this is definitely wrong. Okay, reacts with propan 2-ol to produce this. Propan 2-ol. Yeah, but there's too many carbons here. This is not ethanoyl chloride. Wrong. It reacts with water to produce this. It reacts with water to produce this. No, it produces a carboxylic acid. Why would it produce an aldehyde? Yeah, so this under water will just give you this. Yeah, why would we do that? Wrong. I'll pick A. Okay, 24. In the gaseous state, molecules X, Y, and Z behave as Lewis bases. In which order do the base strengths of X, Y, and Z increase? Base strength increase? This is definitely the weakest base. So I'll put Y first, definitely. So this is wrong. Why? Because this lone pair just delocalizes in the benzene ring. The other ones, this has 2 electron donating groups. This only has 1. I would probably pick X as the strongest base. Yeah, so I'll pick B. Okay, next. Student plans to prepare a sample of C6H5CH2CO2 CH3 in a 3-step process. 3 routes are proposed. The intermediates P and Q are not necessarily the same in each route. Oh no, this is such a long question. Okay, I've got like 20 minutes left. Sample of this, and then they say which route would be successful. Oh man, I have to like look at each of them. Okay, so this is a nucleophilic sub. Alright, so this would produce like something like this, and then this will, under H+, this will do acidic hydrolysis. So this Q would then suddenly be like, okay, and then this with CH3OH concentrated, okay, this esterification. So this in the end would produce something like this, which is C6H5CH2CO2CH3. Yeah, this looks correct. Okay, let's look at 2. This is NaOH aqueous, so it does a nucleophilic sub. Okay, so this will give you something like this OH. And then K2Cr2O7 H+, yeah, you oxidize it, so it just becomes a carboxylic acid. And then under CH3OH, you will get this supposedly at the end. And is this C6H5 no, there's no, this extra carbon doesn't exist. Am I tripping? Yeah, this is wrong. If 2 is wrong and 1 is correct, I'll definitely pick C over here. I don't even look at 3. Let's look at 3. This H plus over here, so this is acidic hydrolysis. Let's just draw this out. So this is okay, and then this P over here is supposed to be like this. LiLH4, it will reduce this. Okay, so you reduce this back to alcohol. No, there's extra carbon. And then CH3OH. Why would this react? Why would this react with this? There's no sense. This is definitely wrong. Okay, I'll definitely pick C over here. 26. Use the data booklet is relevant to this question. The following cell was set up under standard conditions. The cell contains a silver half cell, okay, and a chlorine half cell over here. When this... Okay, this is not standard. Oh, wait. Chloride was then added to a silver half cell. Oh, okay, they're adding it to the silver half cell over here. What effects on the standard electrode potential of the silver half cell and the standard cell potential? Okay, so this sodium chloride will react with the Ag, right? So it's just Ag. Right, because the reduction reaction is just Ag plus to Ag plus E minus. So if you take this out, I mean, if this decreases, then your E value would decrease, right? Because it's not likely to reduce. Is there a trap somewhere? Okay, I mean, they say standard electrode potential. It should have no effect on the standard electrode potential, if I'm not mistaken. Yeah, it shouldn't have effect on standard electrode potential. This is a trap. This has to be A. If it shouldn't deviate. Is the Ag plus... Is this 0.80? Yeah, this is 0.80. Yeah, there's no way. This is... Yeah, this is A. Okay, next. 27. Use of data booklet is relevant to this question. What's the value of delta G for this reaction shown? This is... They give you E naught value. Okay, so just relating delta G and E naught, right? Negative NFE. So this is... How many electrons are there? We have to use the two half equations. So the two half equations are this, and then there's this. So to balance, you need 6 electrons in total. So there's 6 electrons going around this whole circuit right now. So this is 6. Then F is 96500. Then E is plus 1.08. So we can calculate this. 6 times 6.0 times 1.08. This is negative 6.25300 around there, joules, which is A. Yeah, I'll probably pick A over here. Okay, next. Use of data booklet is relevant to this question. Which metal ion is reduced to its metal by reaction with nickel under standard conditions? Reduced to its metal by reaction with nickel. You have to think about the nickel reaction, right? So this is just, and then this is just an E naught value of, this is minus 0.25 V. So if it's reduced to its metal by a reaction with a nickel, that means you're looking for E naught that is greater than negative 0.25 V, right? Okay, so let's look at chromium 2 plus. This reaction is minus 0.91, so this is wrong. Mn2 plus, this reduction reaction is minus 1.18, so this looks wrong too. Sn2 plus, this is minus 0.14. Okay, looks correct. Let's look at V2 plus. To its metal is minus 1.20. Just looking at this, it's wrong. Okay, so I'll pick C. Okay, next. Use of data booklet is relevant to this question. A current of X amperes is passed through an aqueous solution of copper ions for 2 hours. Y grams of copper is deposited on the cathode. Which expression gives a charge on the copper ion? Passed through an aqueous solution of copper ions for 2 hours. Y grams of copper is deposited on the cathode. Okay, so they give you Y grams. You definitely need this, and if X amperes. How do you relate this? Is Q equals to IT and Q equals to NF. This is the two reactions I'll think about. So IT equals to NF. If you want to find the charge on the copper ion, you will find N over here. So N equals to IT over F. Okay, and we know I is X. This is X times 2 hours, which is 2 times 60 times 60. So it's just 2 times 60 times 60 because we need it in seconds. And then this divided by F, which is 96500. And number of moles of copper is just Y over, this is just Y over the molar mass, which is 63.5. Okay, this is Y over 63.5, then because if Cu N plus Ne minus gives Cu, right? If you find the number of moles of copper here, then the number of moles of electrons here, then you can find N, which is just the ratio. So you just basically need the charge is basically equal to Ne minus over N copper. Okay, so this is just X, then it's 2 times 60 times 60, then 96500, and then I need to flip, so it's just 63.5 times Y. Divide by Y. And I'll pick B. Yep, so that's probably the answer over here. Okay, next. Dirty use of data booklet is relevant to this question. Element M has a proton number between 22 and 29. Okay. So proton number between 22 and 29, which row is correct? Density of 1 mole of M compared to 1 mole of calcium. If this is between 22 and 29, then this has to be a transition metal. Okay, testing on transition metals. So density of 1 mole of M compared to 1 mole of calcium. Yeah, these are definitely denser than your calcium for sure. Definitely. I'll definitely not pick this. And the value of lattice energy of MCl2 compared to CaCl2. Oh, this transition metal. Gotta look at the ionic radii. If they have the same charge, you have to look at the ionic radii. Calcium 2 plus is like 0.099 ionic radii. And then the rest, all of the, if you look at the data booklet, all of the transition metals with 2 plus, these are all less than 0.099. Okay, so definitely the lattice energy, right, of MCl2 is going to be greater than CaCl2. So this has to be more exothermic. So it has to be this. Yeah, because the ionic radii of all these MCl2s, of all the M2 pluses in this range are less. So it has to be B. Okay, there we go, time. Okay, so that's that. I'm left with about 9 minutes, okay, for the paper. Whew, I've never done a paper like this in a while. Oh my goodness. Okay, I'm like clearly a bit rusty as well. Okay, I'm clearly a little bit exhausted. Okay, so I'm going to take a quick break, and then when I come back, I'm going to do a quick review of the entire paper as a whole. So over the break, I actually went through my answers, and I actually cross-checked some of my answers through like the answers on Reddit, okay, what people are putting as like the answer key, okay, and I think I am probably 100% correct over here, okay, but if you think I made a mistake or you have any questions on the answers that I provided, maybe do leave a comment down below, okay, and I can probably address them as well. Okay, so I've decided to grade this whole paper. In order to assess the whole difficulty of the paper, I use 3 main criteria. Alright, the first one is application questions. So how many questions actually require quite a deep application level in this whole paper. Okay, the second one is completing on time factor. How many questions are there in this whole paper, right, that actually takes up a lot of time and would be very challenging for students to, even though it's quite easy, right, they waste a lot of time on the question, and that's why it could affect their ability to complete a paper on time. And the last factor is trickiness, right? So a question with like a lot of traps, okay, and they are trying to like lead you towards a certain answer, but actually the answer is not this, and sometimes it might be even more straightforward than that. right? So we're going to assess the paper according to these 3 criteria. For tough applications wise, I think this paper only had about 5 questions, right? So there's actually like question 2, 8, 11, 17, and 29. Okay, they are very tough when it comes to application. Okay, mostly because these are the more challenging questions that I found when I was myself doing the paper, and some of the content that you would have probably seen when you were studying for this exam, right? You might have missed them out, and then that's why you have a tougher time when you encounter these kind of questions itself. Okay, especially like question 29, okay, when you had to like manipulate the equation. Okay, that one was a bit challenging for me, right? That's why I took a bit of time to try and comprehend it. Okay, so for applications wise, I'm going to give this paper a 3. I don't think there were that many application questions that were too tough. In fact, most of the questions were pretty straightforward, and you could see as I was doing the paper, right, I could easily come to an answer, or I could easily come to the method which you need to go to when answering the question. Next factor, completing on time. So looking at overall, right, all the questions that mostly took a lot of time, right, and I could easily say this paper has a lot of questions that would easily take up and suck up a lot of time. Okay, on average, right, a student is supposed to spend about 1.5 minutes per question in MCQ paper. All right, and if there is ever an exceeding of this amount of time, right, these would be the questions that affect your overall time management for the paper. So we're talking about questions 2, 6, 8, 11, 12, 15, 17, 21, 25, 29. Now do notice that I did a bit of overlap with the tough application questions because of course tough application questions do need more time as well to go and ascertain whether you got the correct answer or not. Okay, so an example of these kind of like time-sucking questions, right, are like question 12. Like if you look at question 12, right, this is just an empirical formula question that asks you to go and count the number of carbons and hydrogens, which is really no skill at all, but you have to really properly go and count the number of carbon, hydrogen, and oxygen, right, and make sure you count correctly, right, and then when you count correctly for all of the options, right, then you can come to the correct answer of A over here. So this is why it's a very time-sucking question. And you look at it, wow, there's 10 questions out of 30, right, that can suck your time a lot. Okay, but, right, you cannot forget there were also questions, right, which are called time savers, which were very easy, and you could easily do it under like maybe a minute or sometimes even less than 30 seconds. Okay, so for that, I'm going to give a rating of how well we can complete on time. I'll give a rating of about 5. Now we move on to my favorite part, trickiness, right? I see so many students keep talking about how the paper was very tricky, but honestly, I could only find about 3 questions in this whole paper that were very tricky, namely question 15, question 17, and especially question 26, asking about standard cell potential. If you know, you know. So these are very tricky questions, and a student who is not very careful would most likely get these kind of questions wrong. But it's only 3 questions out of 30. So I'll say the Cambridge Examination Board was pretty fair. They didn't put too many tricky questions, alright, so that the weaker students could still have a chance to perhaps get a higher score for this paper. So overall for trickiness, I honestly think, right, it's about 1.5. So overall difficulty, 3.2 out of 10. Everyone, I have to say that honestly, I don't think this paper was very difficult, especially after doing this already, right? I think that is maybe a bit challenging to complete on time, but there were actually quite a few questions, right, which were just plain giveaways, and they were very easy to spot, like the method, okay, or very easy to find the answer, right? And most of these are like, for example, if you treated it like an open-ended question, right, I think you'll easily be able to get the answer as well. And even though there were some tricky questions here and there, right, even if you don't get those, right, remember, our aim is not to get 100%. Our aim is to secure that A for chemistry. I asked myself, if a normal student who worked quite hard for chemistry, will they be able to get an A, considering that they properly studied all the topics and did enough practice and actually completed all the TYS MCQs? I'll say Yes, I think a normal student can easily just get an A also. Well, I hope you found this video entertaining and I hope you found this insightful to you. Let me know in the comments as well if you want to see me do more of these kind of like paper review videos so that I can share with you all my honest reviews about them and perhaps even put in more practice as well for my own chemistry sake.